right. So this section is called the definite integral, as opposed to the indefinite integral. So the indefinite integral, which we have previously discussed, is the same as an antiderivative. Okay, so you remember that when you see this little symbol, that's the integral. So if I was going to do the integral of, I don't know, 2x dx, that's just saying that I'm going to do the antiderivative of 2x. Okay. A definite integral is now going to give us a bounded region. Okay. So the cool thing about this, and I'm not going to go into a ton of detail about the y factor, but I'm just going to go through this very kind of quickly. So do you remember how we were talking about the area underneath the curve, right? And we were using the Riemann sum. Okay, so for example, if I was going to find the area underneath a curve, such as 2x, I would take it and I could draw 2x. So 2x would have a slope of up 2 over 1, straight line. Okay, and we could define the region, and let's say we were going to go from, I don't know, 1 to 3. Okay, so 1 to 3 would be this area right here. Okay, well, we could use a Riemann sum and you do rectangles, or we could even do, you could see a trapezoidal would be a great scenario in this particular equation. But once we start to get functions that become curved, we need something that's more exact. Okay, so the idea here is that what happened is they said, okay, we're going to start with using rectangles, right? And instead of using big, thick rectangles, the rectangles that are going to be the most accurate to represent the area underneath the curve are going to be rectangles that have infinitely small widths. Okay, so basically like the width of maybe my pen. Okay, so if I can find the widths of each of those lines, then I'm going to become very close to that actual area. Okay, so what that does is it's the idea of taking a sigma, okay, which is a sum of the rectangles, and combining it. And what they ended up discovering is that the sigma is actually the same as the integral within a bounded region. Okay, so this is the piece that you need to write down. Okay, so, sorry, there's a lot of lines going on right there, but you can see you have an integral symbol. Okay, the new piece of information is that now we have a bounded region. Okay, so the bounded region is listed right after this integral. The upper limit, or the upper value, would be the top, which we represent with a b, and the bottom one is going to be a. We still have our function in terms of x. Okay, so the rest of that notation should not be new to you. Okay, so this lesson is just going to be a very introductory piece of a definite integral, and then we're going to get into the very first fundamental theorem of calculus, which is a definite integral. That'll be the next section. Big, giant idea. About integration, yep.
The term like integral, is that
Integrand? What are you looking at? Oh, of the integral. So that's like a, yeah, it's like an integral. Integrand is another term for integral. It's like the noun, or I don't know, verbiage.
But integral is just another word for derivative, right?
Antiderivative. Okay, you ready? Can I move on?
Wait.
Integrate. Okay, so the integral between an a and a b is basically telling us that that's going to be the area underneath the curves. Okay, so what you're going to add to the end of that is, I'm going to slide, don't worry, it's going to still be there. Don't write that, but see there's the summation idea. So that's why I showed you summation. But don't write that down, don't freak out. See, we're going to get to the good part. We're going to skip all the gross part. Where is it?
Right here. Rules satisfied.
Oh, I thought there was a whole box that said equals the area under the curve. Okay, maybe I missed that. So, anyways, so just say this is equal to the area under the curve. Okay, and I don't know if you need to specify that it is bounded between A and C. Bounded. So you can say between the interval of A to B. Okay, so it has to be a defined region in order for us to find its area. We cannot find an infinite area. All right.
You're talking about area under the curve.
Where'd you find that at? Is it above or below? Down? Okay. I knew it was in there somewhere. Good? Okay, so we're going to use a couple theorems of these ideas. Okay, so you need to write these down. And I'll try to give you some time here. Okay, so these are definite rules, or definite integral rules, excuse me. Okay, so the order of the integration does matter. Okay, so notice that if I have an a to the b and I switch it, that area becomes negative. Okay, so we'll do examples with actual numbers in here. Rule number 2 is giving us a bound between a and a. Okay, so if I was going to go between a and a, we're talking about the distance between my hands, right? So what's the distance between my hands if both values are a and a? Value 0. Okay, for 3, if we have some constant multiplied by the area, we can either leave it inside the integral or we can pull it out. It's just being multiplied by that area in both scenarios. You can multiply by the function, or you can multiply it by the whole area. And then 4 is just, basically you can separate a big nasty polynomial into terms and integrate each piece or add each of the areas together. And then 5 is checking the bounds. So if you're going from A to B, we can add that area to B to C.
Who's kidding? She knows.
Did she?
Although she was always kidding. She laughed about it.
Oh.
Or the opposite. Right?
Yes.
No, you don't need 6.
And I said no. Okay, good. All right, that's good. I'm not that good. So me
All right, you guys ready for an example? Okay. All right, let's see what I can find. There we go. Oh, there's the area under the curve. See, I knew it was in there somewhere. Anyway. Hold on, I gotta find an example like that. Okay, I'm gonna steal this one. Okay, hold on, sorry. Thought I had this ready before, but I did not. Okay, so here's what they're going to do is they're going to use some kind of like generic functions or function. Okay, so in this scenario, okay, they're just using f of x to be some function. Okay, and then they also have g of x. Okay, so this says, is everybody looking up? There we go. Okay, so for this one, we have an area that exists between 1 and 2, and the area for that one is -4. So when they give us a negative area, what is that telling us about the function? It's below the x-axis. So most of this area exists, or this line exists below the x-axis. It is possible that some of it exists below and some of it exists above, but more of it would be below. Okay? The area from 1 to 6, or excuse me, from 1 to 5 is 6, and then for g of x, a different function, the area from 1 to 5 is 8. Okay, so we're going to answer these, what do we got, 6 questions here. Okay? So using this information, can you tell me what the area of g of x is between 2 and 2?
No.
Okay? Yeah. The area between 2 and 2 is nothing, right? My two bounded regions are the same. The area exists below the x-axis. Yep, number 9.
Black hole.
Can you not see it? Well, you're using 9, the stuff given in 9, so 9 has 6 parts to it. You see? Hold on, I gotta close this out. My pen is not working. Close. I swear this only happens in this class. Does it happen? Come on, pen. There we go. All right, let's see if I can do that up here then.
I don't know if this is there we go. Like that.
Okay, let's try B. Okay, can you tell me what the area of g of x is from 5 to 1? Okay, good. So notice that the only thing that is different between those is that they switched the a and the b. So when they do that, it just makes it a negative area. So b will be -8. That was good. Okay, what about C? So we have 3 times our function of f of x between the values of 1 and 2.
-12.
-12, good, because I would just take my area from 1 to 2 of -4 and multiply that by 3. -12.
But what about D?
Okay, what about D? What is the area from 2 to 5? Okay, so how could we figure this out? We have 2 areas for f of x. The area from 1 to 2 is -4, and the entire area from 1 to 5 is 6. So what would the area from 2 to 5 be? Okay, so would you agree that the area from 1 to 2 plus the area from 2 to 5 should equal our entire area? Okay, so I can think about this algebraically if you want. You can say that -4 plus, we'll call it x, is going to equal our entire area of 6. So what is the area from 2 to 5? 10. Do you see what I'm doing?
No.
So, okay, so do you see how this is an entire region from 1 to 5?
Yes.
This is the whole region. So if the area from 1 to 2 is 4, and the area from 2 to 5 is something that I don't know, then if I add those 2 areas together, it's going to equal our total area. Okay? So that I can set up an algebraic equation, and I can call that 10.
Would it?
I would figure between 5 and 2.
Because you remember you have that negative area that exists below the x-axis. So negative area exists. Okay. What about E? What is the area from f of x minus g of x from 1 to 5? Good, so I would just take my area from 1 to 5 of f, which is 6, and then subtract the area from 1 to 5 of g, which is 8, and I get -2. Okay, what about f? What is 4 times the area of f from 1 to 5? Okay, so you have from 1 to 5, you're going to have 4 times the area of f, which is 6. That's about 6. Minus the area from 1 to 5 of g, which is 8. So we basically get 24 minus 8. All right, we good there? Of functions? Oh.
One's like 3, and then one is like 2, 3.
Not entirely, but I think if the whole area was given from 1 to 5, they wouldn't ask you to find 1 to 3. Unless they gave you a chunk between 2 and 3 as well. You know what I mean? Like, they'd have to give you more information. Okay. So the second half of this is now doing this by drawing the function and doing it geometrically. Okay. So we're going to start by finding the area of our function between -2 and 4. Okay, so for us to do this, we're going to have to put our phones down first. There we go. Okay, and we're going to start by drawing a picture. Okay. So for number 15, I'm going to draw this right here. Oh, come on, pen. Can you do this on a calculator? Oh, good. Alright, I'm going to have to do this over here. Okay, so if I draw this line, okay, if I was going to draw x over 2 plus 3, what does that look like? What kind of line? Girls, put that away. 1/2 x plus 3 straight line, so it's up 3 units, right? So you might want some graph paper for this section, it's up to you. Okay, and then we have a slope of 1/2, so it goes up 1 and over 2. Okay, so we're going to draw this line, and we're looking specifically between the areas of -2 and 4. Okay, so I want to make sure that my lines are pretty good here. Okay, so there is my entire function, but I'm only going to use the area between -2 and 4. So if this is -2 and this is 4, I'm only looking for this region here. Okay, so using my knowledge of geometry, how could I find that area? What shape have I just created? It's a trapezoid. Okay, so how do I find the area of a trapezoid?
It's the height.
1/2 times the width. Okay, so you can say area equals 1/2 times the width. What would you say the width is? So it's from -2 to 6 or 4.
6.
Yep. 6. There should be a parentheses, sorry. Okay, and then I add my 2 heights at those spots. So what's the height at -2?
2.
Okay.
Wait.
Yeah, you're right.
But isn't it not?
No, because if I plug -2 in here, I get -2 over 2, which is -1 plus 3. Okay, and then if I plug in 6, what's my height at 6? So I can go 6 divided by 2, which is 3, 3 plus 3. Those are, oh my gosh, those are parentheses. Okay, so if we add that together, it's not absolute value. It's not absolute value, it's just the pen won't drop. So we have 3 times 8, right?
Yes.
3 times 8, which makes...
Oh, is that a 2?
Wait, it's not absolute value? No, it's not absolute value. There we go. There we go. Sorry, my pen is broken. Okay. Should we do number 17? Would you be okay with graphing that function, or do I need to go over how you would draw that? Go over it? Okay, so we'll say this is question 15. That's another. Okay, so 17. Okay, so does anybody know what the square root of 9 minus x squared is?
Probably 3.
Or 3 minus x.
Ooh, okay, now this is a very common mistake that I see. You cannot take the square root of each of those terms because there's a minus in the middle. So do you remember what a square root function looks like?
It's like
Kind of like
Kinda.
Oh, it's on its side.
Okay, you're getting closer.
Like that.
Here, let's type this one in the calculator. See if you can remember this. I'll let you use a calculator for a few of them.
We can't use it on that.
Drop the bottle. Yeah,
Yeah, you can. So we have the square root was 9 minus x squared, right? Squared. Zoom. 6.
Are you ever gonna take our calculators away again?
I don't know. I'm decided yet. So, what does this look like? It's a semicircle, and it is exactly half of a circle. Not only that, but it goes to the left 3, it goes up 3, and to the right 3. It is exactly half of a circle.
That would be 3.
So
can't you just take the
if I'm
area
going from -3 to +3, which is exactly where those intersect, right? How would I find an area of half of a circle?
So why don't you just take the area of the circle and
Take an area of a circle. And then just cut it in half. So what is the area of a circle?
R squared.
Okay, so it would just be 1/2 of pi. And what's my r in this case? 3. So 3 squared. Okay, so what would you call that? Keep it in exact form. 9 halves pi. 9 halves pi. So you probably could get away with calling it 4.5 pi, but this is better. Okay? Do I need to keep going, or do I need to cover absolute value? Do you remember how to draw absolute value?
yeah, it's the V.
The v's, yeah. So absolute value, that would just be a v that's centered right at the origin with a slope of 1. What do you got, Sid?
So can you like one of the either 1 through 8 and it's like zero.
Oh, we're skipping those.
Thank God.
I was gonna ask about this one later.
Wait, so then would 21 be an upside down one?
Yep, that's moved up 2 units. So it's up 2 units, upside down, slopes of 1.
And if it were to be like left or right at the inside, like
Yep.
negative?
Yes, you can get negative areas. So remember, any area that exists below the x-axis is a negative amount of area. So you might see that. Okay, are we good? You guys got this? I'll take that as a you got it. Okay, so the assignment that you're gonna, oh, I do have 2 right there. I don't want it to be a 2, I want it to be a 10.
That's why I was looking at the reason.
You want to do it?
So let's change that from,
You want to do 2 by 10?
no.
No.
I like that.
10. 10 through 22 evens. 10 through 22. Let me just double check and make sure it looks okay. Oh yeah, that's good. And then this little section right here. So the only difference right here on this little section is that instead of writing it in integral notation, we're still doing the same thing, but they're binding the A and the B using a different notation, right? So like for 56, you're just doing the integral notation of this would just be the integral from what? From 0 to 3, yeah. And then what would my function be?
X minus.
Negative x squared. No, you don't do it. You're not doing any calculus right now. It is just strictly finding areas. So you're using your geometric knowledge to find the area underneath the curves. I'll show you how to do the curvy ones later. That's the next section. Okay, so it should be in OneNote. There you go. You guys still have like 40 minutes